Okay, so this is our Simondon reading group. Picking up, we're continuing Imagination and Invention. We're picking up from page 152 of the translation. So we're on part 4 on invention, and so last time we're continuing with this sort of more and more elaborate forms of invention that we've been looking at, primarily in various animals. In terms of like animal psychology, what types of behavior different animals are capable of. And so last time we looked mostly at the subsection on instrumental mediation. So essentially tool use in animals. And of course, there's a sort of tradition according to which tool use would be the distinctive property of human beings. That so that Simondon points to this term homo faber. I'm not sure what the origin of that term is. I think it's the Stoics maybe introduced that term, but it's this idea that the human being is essentially the tool-using animal, and other animals would not use tools. And that has turned out, of course, to not be correct at all. There are many animals that use tools, and in a variety of different parts of the whole animal kingdom. So like you can think of primates, for example, using sticks to extract ants from their nest, or using rocks to break open nuts. So those are some famous examples. But there's also birds of various kinds that crows, for example, will pick up a shell of some sort of like a clam or something like that and drop it on a hard surface to break it open. And in experimental settings, we talked about this. Crows will often exhibit pretty sophisticated tool, like second-order tool use. So, like one instance that I mentioned last time was a study where a crow has to use a small stick to grab a bigger stick, and then use the bigger stick to grab a piece of meat. So the crow has to figure out, that the bigger stick would serve to grab the meat, and then that the smaller stick can serve to grab the bigger stick. And so it has to like make two sort of steps in instrumental mediation. It has to understand the relationships between all these different terms at the same time. And then even a variety of insects that only have a few thousand neurons and have like a relatively small brain. These animals are capable of tool use. So Simondon talks about ants that use their larvae for as like a weaving tool. So they like take a pair of leaves, and the larva extrudes a kind of filament, and then they use that filament to sew the leaves together. There's all kinds of other instances of insects that use elements of the environment as a tool of some kind. The question always arises in these cases as to what extent is this a real invention, or is this some sort of like pre-programmed behavior, like what is normally known as instinct. And it's always difficult to prove one way or the other. And especially it's difficult to show that it's an invention. You have to sort of prove a negative. You have to show that this is not a species typical behavior. And so it's always difficult to prove a negative. But in certain settings, you can like in an experimental setting, you can set up a situation that is so untypical for that organism that you can sort of safely assume that this is a novel situation. It's not something that the animal evolves to deal with. And so like the example, one of Simondon's examples here is these beetles that bury dead animals. They sort of dig underneath the animal until the animal sinks into the ground, and then they I think lay their eggs inside the rotting carcass. So in this one instance, the dead animal was tied to a stick or something, something it was sort of supported so that it would not sink into the ground. And so the beetles start digging around the animal, but then once they sort of realize that the animal is not sinking into the ground the way it normally would, they do a bit of exploration and then find the string that's tying the animal to the stick, and then they cut the string, and then the animal falls into the hole that they've started digging. So clearly in the wild, in the sort of normal environment of beetles, they don't come across animals that are tied to a stick. So this is an unusual situation where the beetle has to adapt its behavior in such a way as to produce the desired results, even though the object is behaving in an unusual way. So, I mean, to some extent, in this situation, we can see that there's a certain flexibility of the animal's behavior. It's not just sort of a preset program that is just sort of released by seeing a dead animal. It has to, like, the animal is capable of adapting its behavior to changes in the environment or unusual aspects of the environment. And so this is a kind of invention for Simondon. And yeah, so part of what makes something an invention that Simondon described in this rather dense third subsection that we read at the end of last session, part of it has to do with being able to organize with the way that the images are organized together. So he talks about, like, as a sort of analogy here, is that we have if we look at a map of a space, our mental image of this map, our visual image allows us to navigate that territory. So our behavior on that territory is going to be more adaptive. We can more easily reach our goals by virtue of having this mental image of the map of the territory. Whereas if you just sort of drop someone off in the middle of a landscape in a city or a forest or whatever, and they don't have that map or haven't internalized the image of that map, then their navigation in that territory is going to be much more difficult. And so likewise, he talks about how animals have to learn how different objects behave in order to have an inventive relationship to that object. So he talks about this example of apes in a cage that are given, like, a bunch of boxes, and they just sort of play with the boxes. They, throw them around, pick them up, stack them on top of each other, etc. And then later on, after they've had a chance to explore the boxes, they are presented with a banana or some other desirable food at the top of the cage that they can't reach. And the monkeys or apes that have had the opportunity to play with the boxes figure out that they can stack the boxes on top of each other and climb on top of the boxes and grab the banana, whereas the monkeys or apes that have not had this opportunity to play with the boxes don't figure this out. So again, this sort of undirected exploration of the properties of the objects is a prerequisite for the capacity to invent a solution to this problem using the boxes. We talked about this last bit about how to carry out an invention, you need to have some sort of balance between the affective charge of the situation that you find yourself in. So in the case of the apes, it's the desire to reach the banana. And this has to be sort of counterbalanced by the sort of unpolarized or low affective charge exploration behavior. So all the images, visual, tactile, etc., of the properties of the box that have been acquired through play. So these two sides have to sort of balance each other out, and it's only in that situation that an invention can happen. Whereas in a situation where the affective charge of this desire for the banana, or any sort of situation where there's a strong attraction of a goal of some kind, if you don't have those prerequisite exploratory images to balance it out, you end up getting sort of stuck. You get sometimes we talk about tunnel vision, like you only are sort of seeing the goal and how desirable it is, but then you don't have a sort of counterbalance in those prior exploratory images to allow you to invent a solution. And so an instance of this that he mentioned earlier is cats that are in a spiral-shaped maze. If the food is in the center of the spiral and the cat is outside, the cat is able to keep going around the spiral till it finds the center and reach the food. But if you have it the other way around, if the cat is in the center and the food is on the outside, then the cat is not capable of solving this problem because it has to keep getting further and further away from the food in order to finally exit the spiral and reach the food. And so the cat is sort of stuck in this too strongly polarized situation of like wanting to get as close as possible to the food or wanting to go directly towards the food, and it can't bring itself to distance itself from the food provisionally or temporarily in order to actually reach it later on. So this is an instance of that sort of tunnel vision where the animal can't sort of repress its desire to go directly towards the goal and solve the problem by its knowledge of the situation. So that's about what we saw last time. So if I can get a volunteer to read, let's see, the first page of the next section from the heading B.
I can read. B, Invention concerning signs and symbols, subsection 1, objective metrological formalization from technics to science. How did the shift occur, especially for humanity, from concrete situations to a symbolic formulation that enables the solution not only of a countless diversity of practical problems in each situation, but also of general and theoretical problems for which real difficulties figure as particular cases, as was the case since antiquity for many problems of mechanics or hydrostatics? We can surmise that this shift from particular concrete cases to general and theoretical cases is effectuated on the basis of action by the intermediary of the partially theoretical and abstract formalization that the use of living auxiliaries in an action requires, auxiliaries whose actions one must organize in relation to a goal through commands and a univocal and coherent system of directing data toward the execution of a task. So long as each individual imagines, invents, and executes, practical thought can remain implicit, since it does not go beyond the operator who is the milieu of formalization and execution of the project and its realization. The use of domestic animals to carry out a task already requires that the person who directs them has a more theoretical representation of the activity of operators, of the application of forces, of the resistance of masses, and of the direction of tools. But insofar as the driver stays by the side of the auxiliary animals, the effort of symbolization does not need to be developed into an independent system of signs. By contrast, when an individual calls upon others, servants or slaves, to execute a task, the transmission of commands cannot remain a step-by-step subjugation. In order to make the organized efforts of a team coherent, in order to synchronize activities and harmonize fragmentary executions, a communicable and thus expressible and formalizable conception of the project as a whole is necessary. Recourse to abstract representation begins with the use of domestic animals and becomes fully developed with slavery or forms of labor involving subordination and thus a formulation of the task in a univocal way through a system of commands. Architecture, in the sense of construction by a team with a leader, shipbuilding, or navigation are techniques which have quickly developed the abstract positioning of problems. We sense their influence in the stereometry of the ancients, as well as in formulations that aim, in operative terms, to construct with a given component or to trace a further line with specific properties. The form of the given command has remained in the style of geometry for centuries, likely because it incorporated in its content a set of statements playing a role in the transmission of commands of rational execution. The ruler and compass are instruments of execution, even if at a later stage of research the geometer is for himself as one person, the one giving the command and the one seeking to execute it with his own ruler and his own compass. Order and organization, commands given, and structures of execution happen to be formalizations of the task in accordance with the exigencies of information transmission, of the one who knows and wants the one who knows, of the one who knows and wants to the one who executes and obeys. This seems like one of those paragraphs that we could just spend kind of the whole time talking about. So it's very dense and rich, but the idea here basically seems to be that the development of these formal languages arose in these concrete situations where commands needed to be communicated to presumably people who couldn't be directly monitored. And so it seems like he's arguing that even, like geometry, or at least the formalization of mathematical notation, or maybe the form of the arguments that you find in like geometry texts. I don't know if he has something like Euclid's Elements in mind. Originate in these social situations where someone is giving a command to subordinates.
Yeah, I think here we can definitely think of the passage in Individuation when he talks about how the hylomorphic schema is a slave owner's mode of thought, essentially. So in that passage, he talks about how the slave owner buys a bunch of clay and tells his slaves make a bunch of bricks out of it, and he has in mind, he has this form of a brick, this rectangular shape. So this form is what he communicates to his slaves. He says, this form, this shape is what you need to impose on this matter. And so here we can see a similar type of so this sort of formalization is happening in a similar way here, in the sense that the formal side of language or thought, the capacity to extract from concrete situations a form that is common to several different situations. So like the shape of a brick is not just the shape of this one brick, but of many bricks. So this sort of formalized thought, this thought that applies to many situations by virtue of their form, this arises in a situation where you have to communicate a command, or where there's a social organization of subordination, where the one who sort of plans the work is separate from the one who executes the work. So yeah, and then in the case of geometry, so he mentions that in sort of the future development in when geometry sort of arises as a specific science in ancient Greece, you have the person making the command and the person executing the command coincide. But we can look at sort of the prehistory of geometry. So in Egyptian mathematics, for example, it's often, geometry is often presented as a set of problems. So it's like, given a field of size X, a field of area X, how do you construct a field of area 2X, for example? Like, what are the measurements of the field with area 2X? So like it's a clearly concrete problem, and it's and I mean the etymology of the term geometry comes from like it literally means land measurement or earth measurement, and so this is the type of problem that geometry arises out of, is measuring the fields that belong to particular people, measuring the sides of a pyramid, or like the amount of bricks that you need to construct a pyramid or some structure of some kind. And so these sort of concrete problems where someone, the architect in sort of the broad sense of the term, anyone who has a sort of conception of what the goal is, that person has the plan in mind and has to communicate it to someone else who executes it. And so in this situation, you have to extract the form of the situation, the sort of key property. So here, geometrical form is sort of the paradigmatic instance of this, but it could be some other type of form, other type of sort of essential properties of a situation. You extract those essential properties and you communicate only that to someone else. And because it's formalized in this sense, it's not tied to any one concrete situation anymore. So the architect who designs a pyramid in one city can move to a different city and use the same design and have someone else build a pyramid of the same form in a different location. So these forms are sort of reusable or re-instantiatable, I guess you could say. You can instantiate the form more than once. And so he mentions later in geometry, you have, like in Euclid, you have like problems like given a line to draw a circle, or given a line to bisect that line, for example. I think it's the first proposition of Euclid, if I remember correctly. Here you can see that there's a sort of command that, I'm giving you a line and I want you to divide it into two equal portions of a line. And then in this case, in geometry as a science, as it appears in ancient Greece, as opposed to like a practical art of measuring fields and buildings and so on, geometry as a sort of independent science, in this case, the person giving the command and the person executing the command coincide, so it's the same person doing both. But this is a sort of idealization or an extension of the initial situation where it's one person who comes up with the plan and has the form in mind, and then communicates it to someone else who executes that plan. Right, and Angus has pointed out in the chat here that in that passage in Individuation, when he talks about the hylomorphic schema, he emphasizes that there's a sort of epistemological deficiency of the hylomorphic schema in the sense that it only looks at the form and matter, and it doesn't look at the actual interaction by means of which form and matter are sort of joined to each other. So in the case of the brick making example, it's just this rectangular shape, this abstract rectangular shape of a brick, and the matter, the clay, and they're supposed to be, you're supposed to impose this form on the clay. But the actual process of taking the clay, sifting it, moistening it in the right amount, with the right amount of water, packing it into the molds, pressing the molds and allowing it to dry, etc. The whole process through which the form incarnated in the mold is imposed on the matter is sort of left out of the picture and becomes this sort of obscure intermediary zone. Whereas here, in this text at least, he's not emphasizing that epistemological deficiency. He's talking about he doesn't want, like when he talks about the hylomorphic schema as and he criticizes the hylomorphic schema, he's not saying it's like stupid or useless or something along those lines. He's emphasizing a weakness of it in that text, but he's emphasizing why it has had so much power over the centuries, why Western science focused on this hylomorphic schema for 2,000 years or so, and part of it is this capacity to communicate something about a situation, to grasp the form, the essential properties of a situation, and make that communicable to someone else, so that they can execute the action that corresponds to that form. So this is like the positive side of the hylomorphic schema. It's capacity to communicate the essence of a situation without the sort of unnecessary details. So that's what he's emphasizing here, whereas in Individuation he emphasizes the limitations of this schema and why it's not sort of ultimately adequate. Okay, so let's go on to the next page. 61, do you have a mic? Are you able to read?
Can you hear me?
Yes.
Okay, sorry, I didn't have my headphones in, but yes, I heard you. Okay. Oh, let me get I'm looking through like 5 PDFs right now.
Yeah, so we're at the top of page 154 of this one.
I don't have the same pagination. What's the first words of the paragraph? So I don't.
Oh, right, yes. So it's like a page into section B. The first line is one particular aspect of the formalization.
Okay, I found it. One particular aspect of the formalization of tasks towards the transmission of commands becomes visible with the emergence of complex automatic machines capable of receiving all of the commands before the start of the operation in the form of data and rules. It was then necessary to reinvent logically and in an explicit way the activities practiced by humans according to the semi-implicit, semi-explicit rules. For instance, one of the first chess-playing machines obeyed all of the codified rules of the game of chess, but would place 2 or more pieces on top of each other on the same square. This rule, an implicit part of practical knowledge, had not been included in the given system as a command to the automatic player. Only after succeeding in the complete transmission of the rules of the game of chess to an automatic machine was the system considered fully formulated. Recourse to an instrumental mediation in the form of another living being or a machine provokes, through the recruitment of supplementary effects that arise, a uniform and explicit translation of the terms of tasks and problems, which represents a reinvention of operative modes that renders them independent of the subject and prepares the existence of an independent world of invented reality. Abstract formulations of geometrical problems in analysis became universalized at the time when the design of machines capable of tracing the set of all the curves was being sought. A supplemental aspect of the necessity for formalizing operative modes, involving their explicit reinvention and preparing their objectification, is that of educating children or adults by means of clear expression rather than direct learning practice and manipulation. The recipe must be converted into a logical modality expressible in numbers and figures. This difficulty is so great that it often leads to, quote, theoretical, that is, simplified formalizations, and to presentations that are merely pedagogical. However, the recognition of the logical value of inventions and of the possibility of clearly representing operative modes in a universal language coincides in Western cultures with the movement of progress during the Enlightenment. See in particular the Encyclopedia of Diderot and D'Alembert as an example of explicit expression of the operative modes of professions. The quest for precise modes of expression integral to techniques, has led to the universalization of units of measure for the sake of homogeneity and univocity, and of the internal system which connects them to each other, decimal metric system. Metrology is still not a science in the sense of a universal symbolism of operations of conversion, but it prepares instruments for and opens a functional domain to it. Metrological universalization enables one to measure quantities and discover constancies through the conversion of one concrete form into another, a source of invention. The idea that nothing is lost and nothing created, whether in terms of matter or energy, translates first a metrological ideal, extended to the whole universe. A large number of inventions figure as an organization of conditions of constancy, of conservation of energy or of matter in spite of changes from pluses to minuses or changes of physical state. Hence, cable cars in which one end of a cable is attached to an ascending car and the other to a descending one implement an invention by the maintenance of a constant quantity of potential energy in the system for cars of equal loads. All the machine has to do is overcome frictions and ensure accelerations and decelerations at the start and destination, since they are not neutralized across cars. The more perfect the development of a symbolic measuring system is, the more compatibility can be carried out by linking perceptually heterogeneous realities together. Hence, the cable car schema, in which compatibility is directly perceptible as ascending and descending motion, can give rise to that of tramway or electric trains coupled to the same electrical circuit. The electrical dynamos of one of these vehicles functions as a receptor, thus as motor, while those of another functions as a generator, thus as brake. A reciprocity, which produces the same conservation of mechanical energy now through the conversion of electricity, as that of the cable cars, but here extending compatibility to synchronized acceleration and deceleration. A third threshold could be crossed through a second conversion, now into chemical energy in a battery, since the synchronization of the ascent of one vehicle with the descent of the other, or the slowing down of one with the acceleration of the other, would no longer be required. Metrological symbolism, in its extension, enables the comprehension and invention of ever wider compatibilities. With cable cars, it is not only synchronization that is required, but also a parallelism and proximity of routes. With dynamos, synchronization is still required, but not proximity. With buffer batteries, neither synchronization nor proximity are needed to preserve compatibility. I guess there's one concluding paragraph here. The cases of cable cars and the dynamos of tramways are merely pedagogical, that is, simplified, yet they nonetheless contain real invention schemas of the 19th century belonging to the framework of applications of the principle of the conservation of energy.
Right, thanks. Yeah, that's one of our famous page-long paragraphs that our friend Simon don't like so much. Yeah, so here So this is something that, again, in individuation, he talked about this encyclopedic mode of thought that takes some sort of practical knowledge. So the skill of a craft, for example, shoemakers or woodworkers or whatever, metalworkers, these sort of particular craft skills that have, the person who exercises this skill has all sorts of implicit knowledge of the properties of metals, for example. If I put this type of metal in the fire at this angle, then it, has this kind of results. These sort of implicit craft skills, the encyclopedic mode of thought will sort of translate that into explicit knowledge. So it will not just sort of know how to manipulate objects to produce a desired result, but it will extract from this manipulation the properties of the objects that are essential to bringing about this result. So instead of just having a sort of implicit knowledge of how to produce steel of a certain consistency, it will instead look at the properties of minerals and the carbon content that the steel has to have, and so on. All these different theoretical properties, explicitly communicable properties that the material has to have to bring about the kind of result that you're looking for. And so the encyclopédie in the late 18th century is Simondon's sort of favorite instance of this. So it has all sorts of articles about particular crafts that are exercised in France in the 18th century, and all sorts of diagrams of the different tools and machines that were in use. And it tries to give scientific explanations, so theoretical explanations in terms of knowledge that can be communicated of how these different crafts work. And so it's the opposite of a sort of apprenticeship kind of mode of thinking or a mode of appropriation of knowledge. So in an apprenticeship, you learn by observing the master and trying to replicate what the master does, and you learn this implicit craft knowledge, but you may not be able to communicate to someone else outside the craft what exactly it is that you're doing, or why you're doing something in a particular way. Whereas in encyclopedic thinking, the whole idea is to make that knowledge as explicit as possible, so that you can communicate it to someone who hasn't studied that craft. And so this is a kind of explicitation of knowledge, and it requires, again, that formalization, so that the type of knowledge that the metalworker exercises in a particular forge somewhere in France, for example, you can extract from that particular forge and the context of France. You can, like, a different forge in Germany could perform the same actions and in principle get the same results. So again, you're sort of formalizing your knowledge, you're making it communicable, and this allows for the transportation of a sort of technical system from one location to another. And then, so the example, and maybe one thing also I'll mention here is this idea of metrology. So the late 18th century, and then the French Revolution happens not long after the publication of the Encyclopédie. And one of the sort of key lasting actions of the French Revolution, the French revolutionary government, was the institution of the metric system. And so one of the key ideas of the metric system was to replace all of the local weights and measures of, so in France prior to the revolution, each province or district would have had its own system of weights and measures. So if you bring your crops to a market in one town, you would have like one set of weights and measures, and then if you bring them to market in a different town in the next district, you might have a different set of weights and measures. And so comparing the prices is more difficult, and measuring, like, is wheat cheaper or more expensive in district A compared to district B becomes more difficult. And so the idea of a uniform system of weights and measures is to facilitate commerce as one of the sort of key ideas. And so that the whole domain, in principle, the whole world, but at least the whole of France would have one system of weights and measures that would be easy to understand. You wouldn't have to learn, how many feet there are in a league or a mile or whatever. You would just have this constant decimal progression. So you would know exactly how many meters there are in a kilometer just by understanding what the name means. And so these sort of rational systems of weights and measures would facilitate commerce, facilitate technical invention, because you would have parts that would be standardized to the right measurements, for example. And in general, they would be more easily communicable as opposed to these sort of local, particular systems of weights and measures that you only have access to in a particular locality. So this is like the role of metrology and how it ties in with this encyclopedic mode of thought. And then he goes on to talk about this principle of conservation as one of these sort of formal schemas of thought that is used in invention. So he gives like a series of examples of using a principle of conservation to perform some sort of desired technical action. So the first example here is the cable cars. So like these are often used in a mountain setting where you can think of a ski lift, for example, where you have one car or one set of cars ascending the mountain, being pulled up by the cable, while at the same time another car or another set of cars is pulling down on the cable on the other side. And so, in principle, these two sides, if the cars are equally loaded, there's like not extra weight on one side. They balance each other out, and so the only like the motor, whatever kind of motor you're using to actually pull the cable, only has to overcome the friction and doesn't have to lift the whole weight of the car on the one side. So this idea of, or this sort of schema of conservation, you can sort of directly see when you build a device like this, or when you sketch a device like this, you can see how the cars on the descending side are pulling the cable down, and how the cable is then pulling the other cars up. So you can sort of see the whole schema of conservation of potential energy sort of at work in this device. And then he talks about sort of the next stage, the more abstract stage and less sort of immediately visible one, is where you replace the direct traction model with an electric model. So here you have electric trains where the acceleration and deceleration of the trains is synchronized in such a way that the same electric charge is conserved. So one train is braking, and so it's generating electricity by it's sort of transmitting kinetic energy into electrical energy, transforming, I should say. And then the other train is accelerating at the same time, so it's transforming electrical energy into kinetic energy. And so there's a sort of converse transformation happening at the same time on both trains. But of course, this type of system is, in a lot of contexts, is impractical because you have to actually synchronize the two different trains. So you can only use it in like a subway system, for example, where there's a predictable schedule of the trains. If you have like a streetcar where the car might have to stop for traffic, for example, and has a sort of unpredictable schedule, then you have to use something like a battery. So you have a second step of conversion where the electrical energy is converted into chemical energy in the battery. So here again, you're relying on the fact that the energy is conserved. A certain amount is lost as heat in any transformation like this, but the idea is that you're conserving the energy. The kinetic energy becomes electrical energy, becomes chemical energy, and then that chemical energy can be converted back into electrical energy and again into kinetic energy. So there's this constant conversion. There's a conservation of this quantity of energy across the conversion from one form of energy to another. And so this schema of constant conservation of some quantity here, energy, is sort of being used. It's this sort of abstract schema that you can apply to a variety of different types of technical devices. And it's something you can communicate explicitly. You can draw up a diagram of the functioning of a train system. You can explain it theoretically in terms of the quantity of energy and so on, as opposed to something like, I don't know, a crashed water mill, for example, that you might not be able to explain exactly what it is that's conserved and transmitted in this mechanism. So this is like the development of the progress of formalization is a kind of more and more abstract conception of what exactly is conserved and transmitted across these technical schemas. Okay, so I think we have time just for the last section, or the last bit of this subsection here. So I'll read this. As for the conservation of masses, the condition of possibility of measures using the scale as an instrument through the intermediary of weight, or more directly, of elastic systems, it enabled the formalization of the basic metrology of chemistry in the era of Lavoisier, after having rationalized the technical study of combustion for lighting and other oxidations, human respiration. Hence the formalization of operations, useful at the outset as means of communication to give commands or perform an educational training when the operator delegates the function of execution to a third party while retaining the management of the work, detach themselves progressively from this asymmetrical function of communication in order to become a universal and homogeneous symbolic system serving as a basis for abstract operations and providing a higher level of extension outside of homogeneous and concrete situations to the activity on invention. Symbolic formalization, required to cross the distance and heterogeneity between conception and execution, weaves an abstract world of representations of objects and formulas of relations that forms a universal reserve of detours and mediations within the exercise of inventive activity. This first level of formalization, continuous with operative processes of techniques, prepares scientific invention and develops a representation of the world in which knowledge and power are convertible one into the other. We might say that this mode of formalization is subjective, as independent as possible from references to a subject. It tends towards the execution of tasks by an impersonal, non-human, even non-living operator. It is a formalization for any operator whatsoever that provides a terrain for the development of scientific knowledge as a universal system of compatibilities. Right, so here we have the example of Lavoisier. So this was like one of the sort of key developments in chemistry was the use of more and more precise measurements of chemical processes. And this brings about the idea that in a chemical interaction, there's a conservation of mass. So we talked about conservation of energy before, but in a chemical interaction, there's a conservation of mass. So there's nothing produced, there's no increase of mass, and there's nothing disappears in a chemical interaction. This brings about a whole transformation of chemistry in the early 19th century or end of the 18th century, with the introduction of the notion of oxygen and the transformation in the understanding of combustion. So combustion is actually some sort of chemical like carbon combining with oxygen, as opposed to earlier theories that held that there was a substance like known as phlogiston, which was emitted in combustion. So the combustion would be the loss of a substance of some kind. So this more accurate weighing of the elements that go into a chemical interaction allows for this transformation of the whole system of what combustion consists in, and the development of the notion of chemical elements that we have today. And so in these last couple paragraphs in this subsection, he compares the formalization of concepts, this development of these sort of encyclopedic, this kind of encyclopedic knowledge. He compares this to the exploration of a territory. So it's because as an inventor or a scientist, you come to a problem with all this knowledge, this formal knowledge of the properties of different chemical substances, these sort of schemas of thought, like the conservation of energy or the conservation of mass. You bring all of this to bear on the problem, and so you can take these elaborate intellectual detours. You can solve a problem by using a machine that seems that uses chemical and electrical and all these other properties. You can bring this machine to bear on a problem that doesn't have anything to do with those sort of schemas of operation that the machine uses. So yeah, you have this capacity to take this elaborate detour through this theoretical formal knowledge and use these different principles to solve a problem that you can't sort of just read off of the problem. You have to bring this knowledge onto the problem from your prior learning. Okay, so if there's no sort of final thoughts or questions, we are going to have to end here, unfortunately. I have something else I have to get to. So we'll pick up from page 156 next time, and we'll continue from there. So yeah, next week we should be able to have a full session as far as I know. But yeah, so let's meet again next week. So thanks everyone for coming out and for your contributions, and see you next week.